Morning, nerds. I hope that homework went well after yesterday's lesson and the day before, sine and cosine graphing, because today we're going to be talking more about the characteristics of those graphs, and it's actually a remarkably easy lesson. I just got to try to get through it before the lockdown drill begins. Okay, put the pencils away. Here we go. We've already talked about this in the past, but sine and cosine are periodic functions. That means they repeat themselves every so often. This means that the function, I already said that. Yeah, what we know is that the sine of an angle, so here we're talking about sine of angle x, it actually plots the y values as you go around the unit circle, whereas the cosine of angle x plots the x coordinates of the unit circle as you go around the unit circle. I know that's confusing. This is not the x coordinates, this is the x angles. That's how you have to think about that, okay? So as the angles go around the unit circle from 0 to 2 pi, this wave tracks your x coordinates of the unit circle. There, that's what that says. Okay. Boink. So we got our two parent function graphs. We've solved those over the last couple days. Easy peasy, lemon squeezy. What we're going to do is we're going to fill out all the things that we know to be true about them. The key points. I don't have them memorized, at least not as coordinates. I just know where they go. So in order for me to write down these key points, I would literally need to read right off of this picture. So I would draw myself a picture and then read these coordinates. They are 0, 0, then pi over 2 comma 1, then pi 0. The fourth one would be 3 pi over 2 comma negative 1. And lastly, back to the midline, so 2 pi comma 0. Since sine of an angle, sine of theta, is y over r, and since the radius of every circle is a positive number and the radius can never be equal to 0, sine will always be a y value over a number that is not 0, which means it's always defined. So the domain is all real numbers. We've already talked about it, but you can see it in this image, the range from -1 to +1. The amplitude is the distance from the midline to a maximum or midline to a minimum. Doesn't matter. It's the same value, 1. The period length is how long it takes for one cycle, which is how long until it repeats itself, 2 pi. And arguably the most important thing about the sine wave is its symmetry. So I grabbed some scrap paper. You don't need to draw this, but I'm going to draw the sine wave for you, the parent sine wave. Looks something like this. But can we agree that this graph goes on forever in both directions? So then it would go this way as well, right? It would follow the same pattern. So in order to do that, did you see what I did to the paper? I flipped it upside down. But have you noticed that flipping it upside down doesn't change the image at all? Well, that's not true. Flipping it upside down, it does change the image. How do I want to say this? If I were to flip this upside down, this maximum would become a minimum, correct? But if I were to reflect it over the y-axis, this minimum would be right there as a minimum. So if I turn this graph upside down, I get this image in red. And if I reflect it over the y-axis instead, let me draw this blue bump, this blue bump, reflect this blue bump over the y-axis, this blue bump over the y-axis. Holy crap. Reflecting over the x-axis, turning it upside down, gave me the red one. Reflecting over the y-axis, which means reflecting it left-right, gave me the purple one. And be darned if the red and the purple weren't exactly the same. So, negative sine of x was equal to sine of negative x. Does anybody remember what kind of symmetry says reflecting over the x is the same as reflecting over the y? Odd symmetry. The sine function, the parent sine function, has odd symmetry. Isn't that neat? It's a very important concept. The symmetry of sine. Oddly symmetric. You could also say it's symmetric around the origin, which was why me rotating the paper to draw the other half of it worked. It's also sometimes it's called rotational symmetry around the origin. But anywho, now let's take a peek with this cosine wave. It's 5 points. Again, I don't have their coordinates memorized. I have the shape memorized. I would literally have to draw the picture and read the coordinates directly off the picture to pull this off. But I can see them right here. 0, 1. Pi over 2, 0. Pi negative 1. 3 pi over 2 comma 0. And lastly, 2 pi 1. Yeah, I do not have those two lists memorized. I have the shape memorized. I know the period. I know the amplitude. So if tomorrow you asked me to come up with those points, I would draw the picture to come up with those points. Like if you're doing trigonometry without pictures, I don't know how. I can't. I can't even check trigonometry work without pictures. She's giving her the finger again? It's 2 days in a row. Dang. Okay, domain. Just like sine, since the bottom of the fraction is the radius, and the radius is always going to be not 0, you're never going to get a 0 on the bottom, so you are always defined. Just like sine, the range you could see from this picture, negative 1 to positive 1. Here's your midline. And just like sine, the distance from midline to max or midline to min is positive 1. So that's the amplitude. Just like sine, it takes a full 2 pi to repeat itself, so that is the length of the period. However, cosine is not an odd function. Here's a cosine wave. I'm going to do my best to draw it the other way too. I'm really bad at drawing left-handedly, meaning pushing the pin instead of pulling the pin. Oh my God. Yeah, I'm sorry. It's so hard for me to draw left-handedly. But you get the idea. You get the idea, right? Do you see that, barring my drunk left-handedness, that these two graphs are the same? Meaning this thing is symmetric over the y-axis, which is even. So the cosine graph is the parent cosine graph is an even function, is even symmetry. And this is a very, and I mean very, important concept. That means that reflecting it over the y-axis, meaning changing the angle from a positive to a negative, is the same as doing nothing. Cosine of 60 degrees equals cosine of negative 60 degrees. That's really easy to demonstrate too. If you wanted to see it, let me draw my 60 degree angle. If this is 60 degrees, there's always a root 3 across from a 60. It's a 1 next to it and a 2. Negative 60 degrees is this way. But the size of that, even though it's negative 60, its size is still 60 degrees. which means there's still a root 3 across from it. Happens to be negative. But cosine is your x over r. And x was unaffected by going to the quadrant below quadrant 1. So x over r is still going to give me 1/2, regardless of positive 60 degrees or negative 60 degrees. Cosine has even symmetry. That's a big deal. Okay, now, I should have grabbed one more piece of scrap paper. And it's unfortunate that this won't make it onto the video. But we're going to do a show of hands in just a second, okay? We're going to do a show of hands, so I'm going to need you all to pay attention because you're all going to vote for one or the other. Cool beans? Cool beans, okay. Just give me a moment to draw something. I've drawn a wave. Your options are, this is sine or this is cosine. And I'm going to have you raise a hand to tell me which one you believe it is after that person comes into the room, because one more vote. We need it. All right, he's back. All right, Noah, we're voting, okay? We're voting on whether or not this is sine or cosine. So show of hands, if you think this is a sine wave, please raise your hand. 1, 2, 3, 4, 5, 6, 7, 8 of you. 9. Hands are starting to 10, maybe 11. It's like a herd mentality. Okay. So, show of hands, who thinks this is a cosine wave? I feel like a lot of you didn't vote, but I also feel like some of you double voted. Audie, did you double vote? Why? Oh, because it's both. Yeah. You see, there is no such thing as this is a sine wave, this is a cosine wave. It's both. It's both. How are you going to say a graph that's infinite and repeats itself actually starts somewhere? I mean, let me throw an XY axis on here, okay? We'll say this is the y-axis. And we'll say this is the x-axis. And now you're saying, Mr. M, that is clearly a cosine wave. And I go, no, it's not. It's just a sine wave that's been started to the left of the y-axis. Or maybe it actually is a cosine wave, but I started it back here. Maybe, let's really buck the system. Maybe it's a negative sine wave that started there. Or here. Maybe it's a negative cosine wave that started there. You see, it actually doesn't matter. There's an infinite number of ways to write the equation of a graph like this. There's an infinite number of correct sine functions. There's an infinite number of correct cosine functions. And it all just depends on shifting and reflecting. Because the sine wave and the cosine wave represent the same values. They just happen to have been shifted. So by comparing the two waves, you can see that either one can be horizontally translated to get the other one. We call these kinds of things sinusoidal functions. And later on in the notes, we are going to prove that this is a truth. But, I mean, we can just look at it right now. Look at this. Couldn't I easily say that this is actually a sine wave? It's just been shifted to the right. Pi over 2. Couldn't I easily say that this is a sine wave? It's just been shifted left. Pi over 2. This says cosine is sine shifted left pi over 2, which is what I just showed you. We're going to prove it to ourselves later on in the notes, but I mean, I think it's pretty obvious just by looking. You could see it. If you say you started here, you have a positive sine wave. It's just the positive sine wave has been shifted pi over 2 to the left of where it normally begins. How about that? So this is the general form of all sinusoids. Because sine and cosine can be written as each other, mathematicians just decided to say the general term is a sine. But it really doesn't matter. You've got your reflections and vertical dilations, your reflections and horizontal dilations, your horizontal translations, your vertical translations. So transformations that you're used to seeing, obviously you can't have either of your A or B be equal to 0, because if you did, if A was 0, you'd just have y equals 0, and if B was 0, you'd have y equals A times sine of 0, which O is 0 again. So if either A or B was 0, you'd have y equals 0. So that's why that can't be. But they could be any other numbers as long as they're real. Really easy math. Look at the picture and tell me the period length. How long does this image take to repeat its pattern? 1 pi. Look, it's right here. Boop, boop. 1 pi, and that thing repeats. How about that one? How long is that one going to take to repeat itself? Half a pi. Pi over 2, because look. Boop, there it is. So easy. We did this over the last 2 days. Hey, from the equation, how do you find the period length? Well, it's 2 pi over b. Now, technically, it's absolute value of b. But why would you say the length of something is negative? So I don't ever bother with the absolute value bars. But this one's period then is just 2 pi over 5. Look how easy that is. This one's, well, that one might be a little bit more challenging. Oh, you kidding me? The phone's ringing on a short period day. Anyway, as I was trying to say, this could be rewritten as 1/3 x, so that your b value is actually 1/3. Yeah, so the period length for this one is 2 pi over 1/3. But you know, dividing by a fraction means just multiply by the reciprocal. Keep, change, flip. 6 pi. Look how easy this is. This is even easier. Looking at the graph and finding the amplitude. All right, well, the way that I always do this is I track down my midline first and then I count. Sometimes the midline is remarkably easy to see. Sometimes it's not. That one's midline is remarkably easy to see. And then you can instantly tell me that the amplitude is 4, because it goes from 0 to 4. But what if the midline is slightly harder to track down? I mean, there's a way to do it algebraically, and there's the just look at the picture and count method. Let's start with the look at the picture and count method. From the bottom to the top, from -1 to 5 is how long? 6. So halfway through would be 3, right? So if we go from the bottom up 3, we go 1, 2, 3. It puts me right here at y equals 2. Now, to see your amplitude, all you have to do is look from midline to maximum. And you can see that the amplitude is 3. But there's also a way of doing that without finding the midline. What about it? What do you mean to find them and divide by 2? What do you mean? Okay, the minimum is 5, the maximum is -1. If you add them and divide by 2, you found the average, that gets you the midline. I want the amplitude. Or, okay, I know, I said I want the formula for it, the algebra. I said there's 2 ways. I said there's an algebraic way and there's a just count way. I just did the count way. So the formula is max minus min divided by 2. Literally, the distance between them divided by 2. Okay? Does it matter? What is 5 minus negative 1? 6. There you go. So max minus min will always be a positive number no matter what you do. Okay? Now these, the amplitude is just literally on the equation. So hopefully it's obvious that the first amplitude is 4, because amplitude is always positive, and the next one is 1/2. Ta-da! It is that easy. Okay? It is so easy. She said shift. She said now shift. We finally get to put some words to a shifting. I know I've said it before, but a phase shift. So what we're doing here is we're verifying using transformations that this is a true statement. So the first thing it wants us to do is to graph y equals cosine of theta on this domain. Okay, here is my midline, and it's the parent wave. I'm going to do that one in, trying to pick colors that'll stand off of one another. Tell you what I'll do. I'll do it as a blue dotted line. Maximum to maximum. Halfway between is a minimum. Halfway between those are midline hits. Minimum to minimum is also period length. Minimum to minimum is also period length. So this is cosine of theta as a dotted line. From negative pi to 3 pi. Awesome. It says, use the key points to complete the table below. Basically, plug in these values for theta. So let's see what we get. And I'll do this one in green. Sine of 0 plus pi over 2. Well, that's sine of pi over 2. And if you wanted to go back and look at the 5 points or whatever that we had on the very front of these notes, sine at pi over 2 was 1. So let's plot that coordinate, 0, 1. Now let's plug in pi over 2. Okay, 1/2 plus 1/2 is 1, so I have sine of pi. And if you go back to the front in your 5 coordinates, the sine of pi, well, sine is 0 at all pi's. So that's the coordinate pi over 2, 0. Oh my goodness, look what's happening. It's landing on my blue curve. Let's plug in pi. Okay, sine of 3 pi over 2, if you go back to that parent sine wave on the front and look, 3 pi over 2, sine is negative 1. So pi comma negative 1, oh my gosh. I think that you understand what's happening here. It's going to keep matching up. It lands at the exact same points. So we have confirmed now that this is a truth. It's a very important truth. I want to come back to the front. I don't want to write that junk down. Oh, it's already written, right? So we know that this is true, that the cosine wave is the sine wave simply shifted left pi over 2. But why stop there? Why not make a rule for sine of x in terms of cosine of x? So let's come up here. What would I have to do to this cosine wave, I'm pointing at the wrong thing, to say that it's a sine wave? There it is. Go left pi over 2, right? So if I shift my, wait, I'm saying this backwards. I'm saying it backwards. I'm trying to say what the sine wave is, the cosine wave shifted, right? So this one right here is this. So this one, sine of x, if I want to call this a cosine wave, then I would say it's a cosine wave that's been shifted to the right, pi over 2. But here's the thing. This is not typically how we see this identity in textbooks. How do we typically see it in textbooks? Well, let's check this out. Remember that cosine is an even function? What that means is, if I multiply its argument by -1, that's the same as doing nothing, right? So if I multiply this argument by -1, it won't affect this side of the equation. But if you multiply these by -1, this becomes -x, and this becomes positive pi over 2. This is typically how we see these identities in textbooks. And this should make perfect sense to you. Why? Because sine and cosine are complementary functions. That's why cosine starts with the CO. Sine at 50 degrees equals cosine at 40 degrees because they're complementary, right? Sine at 50 degrees is cosine at 90 minus 50, which is 40. And that's why it's typically written that way in textbooks. It's a big deal. Midline. Two ways of finding the midline. You could either just look at the picture and figure out what's halfway through it. Oh my goodness, really? Well, they waited. Okay, fine. I'm waiting too. Halfway through, let's see, from -5, or from 5 to -1, that's a distance of 6. If you go halfway, that's 1, 2, 3. Oh, here it is, right here. There's the midline at y equals 2. And this one, from 2 to -8, that's a distance of 10. So let's see. I got to cut that in half. 1, 2, 3, 4, 5. Right here at -3. Uh-oh, lockdown. Attention staff and students. It's like they forgot to warn us. Hopefully the video doesn't corrupt while we're waiting for it to end. Cool, we're recording again. All right, so we all survived the lockdown drill and the video did not corrupt. So we can continue working. Anyway, where we were was right here. We just counted and we figured out what halfway was in order to find the midline. But just like the amplitude, there is an algebraic way of finding the midline. And you might be thinking, why would I bother? I could always just count. Well, what if the answer isn't pretty? Like, what if it's 3.125 or something like that, and you couldn't just count, okay? And that's why we need to have both use your eyeball methods and algebraic method. So again, if you want to know the amplitude, it's maximum minus minimum, guarantees positive number, divided by 2. If you want to know what the midline is, well, it's in the middle. Yes, Jack? Add them and then? Divide by 2. You literally find the average, because the average of two numbers will always be in the middle. So if you would like to know the midline, you just add the max and the min and divide by 2. For example, this was a 2 and this was a -8. 2 plus -8 is -6, and -6 divided by 2 is -3. So now we have an algebraic way and a use your eyeballs way. Cool beans. Now when it's an equation, life is good, because this is just a transformation. The midline should have been y equals 0. Since it's been shifted down 5, the midline is y equals -5. Since it's been shifted up 4, the midline is y equals +4. And that is the entire lesson. I almost beat the lockdown drill. Appreciate you, nerds.